Good evening, Eddington. This is the end of everything. The fate of the Earth, the fate of the Sun, the fate of the galaxy, and ultimately the fate of the universe. So in a sense, we're going to eternity and beyond, if you will allow me to paraphrase Buzz Lightyear. We'll be having a short prologue, and then we'll be looking at the future of the Earth, Sun and solar system, the far future of what's happening to stars and galaxies, and then we'll be looking at the far, 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 far future and the ultimate fate of the universe. And if that all sounds far too depressing, I'll finish with a little epilogue, which will be on a slightly lighter note. So yes, back in November, I was telling you about the beginning of everything. And I'm not going to recap that lecture so much as to say that we think that the universe began with the Big Bang, and everything that we now see in the observable universe, all 100 billion light years diameter sphere, everything used to be a lot closer. The universe is expanding. Everything that we now see in that huge observable universe used to be just centimeters apart in this cosmic golf ball. The universe expanded, hydrogen was made, helium was made, the universe continued to expand, we had the cosmic microwave background, and we ended up with the universe that we see today. And this evening, we're going to think about how we go from now into the future. And we can't just jump a million years at a time, because that would be not a very sensible way of stepping through the future. So what I'm going to do to try and keep track of where we are in time is to use this timeline across the top there. Each small box represents 10 times further into the future than the previous box. So we can think about what's going to happen thousands of years into the future, or millions of years, or billions of years, or trillions of years. So we're going to use this notation 10 to the power something, 10 to the power the number of zeros in the number, if you like, in terms of years into the future. And acknowledgements to Adams and Laughlin, who wrote a paper 25 years ago on the timescales on which various astrophysical phenomena are going to occur, or at least are predicted to occur. And I've used that particular paper to try and get my slides in the right time order. I'm not going to deal with only the Earth and then only the Sun and then only the galaxy. I'll deal with each particular point in the relevant time scale. So we don't know when stars are going to go supernova. I'm jumping to 10 to the 4 years in the future because I'm skipping over 10 and 100 and 1000 years into the future. Nothing of any great consequence is going to happen, astronomically speaking, on those timescales. Let's assume we don't have another world war. Let's assume the man-made influence on climate change is under control. Stars will probably start to change on a timescale of 10 to the 4 years because some stars will go supernova, but we're not sure which ones. Let's deal with things that we are a little more certain about. So on this timescale of 10 to the 4 years, we know that because of the precession of the Earth's axis, this spinning and the Earth's axis pointing to different parts of the sky, we know this occurs from historical records on a timescale of about 26,000 years. So that means on a timescale of 10 to the 4 years, our North Star is going to change. In other words, at the moment, our axis points roughly to Polaris. It's within a degree of Polaris. In the past, it used to be the star Tuban back in Egyptian days. And in another 10 to 12,000 years, the North Star is going to be Vega. In other words, that's going to make it very easy for Boy Scouts to point out which way is north. They just need to find a really bright star in the sky. That's probably the North Star. It's going to be easier than currently with Polaris. But what are the consequences of the North Star changing? Well, at the moment, the Earth is closer to the Sun, perihelion, during northern winter because of the way the Earth's axis is pointing, as indicated here, pointing towards Polaris. But if the Earth's axis points the other way towards Vega, that means that we are going to be nearer the Sun during northern summer. In other words, the distance to the Sun and the tilt of the Earth are going to exaggerate the seasons. So there are going to be variations in the Earth's climate that are due to variations in the Earth's spin. And collectively, any change to climate that's a result of either the Earth's spin or the Earth's orbit around the Sun are collectively called Milankovitch cycles. We'll hear more about that in a moment. On a timescale of 10 to the 5 years, the Voyager space probes that left our solar system, were launched in the 1970s and are now leaving our solar system, on a timescale of 10 to the 5 years, they'll be passing other star systems. Probably 30 to 40,000 years into the future, the Voyagers will pass into other solar systems. So at the top left of the image, there's Voyager 1. That's heading out in the direction of the star system Gliese 445. And in the bottom left of the image, Voyager 2 is heading off in a different direction towards the star system Ross 248. Pioneers 10 and 11 are also leaving the solar system. They were launched a few years earlier, but they're travelling more slowly, so they will take a little longer. Pioneer 10 on the right-hand side of the image is heading off in the direction of Aldebaran, and Pioneer 11 is heading off in the direction of the centre of the Milky Way. So on these timescales, we would expect the Voyagers to pass through other solar systems. Maybe those solar systems are inhabited, who knows? Maybe they're not. Maybe Voyagers will just pass through the solar systems and head on to the next solar system in another 30 or 40,000 years. We know from historical records that the Earth has gone through repeating cycles of ice ages, glacial cycles and interglacial periods, the warmer periods in between ice ages. And these tend to occur on timescales of order 100,000 years or so. We know that the Earth entered an interglacial phase relatively recently, and so we're due for an ice age in another 100,000 years or so. This repeating ice age every 100,000 years is another manifestation of Milankovitch cycles. It's because of changes to the way the Earth is orbiting the Sun, the elliptical orbit of the Earth around the Sun. Still, on a timescale of 100,000 years into the future, we know that the Earth is slowing down. Its rotation is slowing. It was quite fast when the Earth was made a long time ago, but it's now about 24 hours. Every once in a while, we add a leap second into the clocks to keep the rotation of the Earth synchronized with our clocks, or if you prefer, to keep our clocks synchronized with the Earth. If the Earth is slowing down, then in another 100,000 years, we'll need to add leap seconds, not once every few years or so. We'll need to add a leap second basically every day, because the Earth will have slowed at this point to a rotation period of about 24 hours and 1 second. So leap seconds would still be useful, but we'll need an awful lot of them. Still on timescales of order 10 to the 5, we can't be certain, but we think that stars like Eta Carinae, for instance, a very massive and apparently quite unstable star in the southern hemisphere, we think this one is probably going to go supernova. It will probably not take 10 to the 5 years. It will probably go supernova on a shorter timescale, but we can't really predict it with any accuracy. Eta Carinae has been shrugging off its outer atmosphere for hundreds, if not thousands, if not tens of thousands of years, and that's produced the nebula that we can see surrounding the star. So we know it's unstable, we know it's shedding a lot of mass, and this star is massive enough that if it does die, it will probably die as a supernova. So we're keeping an eye on that one. It might be beaten to the punch by Betelgeuse in the northern hemisphere. This is an indication of what that might look like. This is an astrophotograph in which the photographer has artificially enhanced the brightness of Betelgeuse and produced something that would be spectacular by night and probably visible by day as well. Betelgeuse being about 600 light years away, that's about far enough away that the supernova would be spectacular, but not, to us, dangerous. But the death of some other stars might conceivably be more dangerous than Betelgeuse going supernova. For instance, Wolf-Rayet 104, A Wolf-Rayet star is a star, again, a very unstable star. They're rapidly rotating. This particular one is 7,000 light years away, 10 times further away than Betelgeuse. But it's thought that when this star dies, its death may result in a radiation burst even more powerful than a supernova, because rapidly rotating systems like this often produce jets. And if that jet happens to be pointing towards the Earth when it dies, well, there could be a gamma ray burst, which is significant. It could, in principle, sterilize part of our biosphere. It's difficult to be precise. It would have to be rather unlucky for that jet to be pointing directly towards the Earth. Hopefully, it's pointing a few degrees away, and this will not be a problem. But we've got to watch out for these things. On a timescale of 1 million years into the future, we know the stars around us are going to change their position. We, like most of the stars around us, are orbiting the Milky Way with a period of about 200 million years or so. So as we all go round the Milky Way in our own independent orbits, every once in a while we're going to happen to get close to some of our neighbouring stars. And the Gaia spacecraft has been measuring a lot of stars very accurately, their positions and their motions, and we think that the star Gliese 710 is going to pass very close to us in 1 million years or so. So close that it will actually come within our Oort cloud. The Oort cloud being a large sphere of trillions of icy particles, comets. When Gliese 710 enters the Oort cloud, it'll disturb a lot of these objects, and some of them will come raining down into the inner solar system. So the passage of this star will probably result in naked eye comets every month for possibly 1 million years or so, until Gliese completely leaves our solar system. It's interesting to note that for a while, in 1 million years or so, the solar system will actually have 2 suns, a bit like other systems that we know about. Perhaps it won't look quite like that, but it's still interesting to have a 2-sun system. Still on a timescale of 1 million years into the future. Is this picture of Meteor Crater, Arizona supposed to indicate that we can expect an impact like this every 1 million years? Well, no, not really. This picture is being shown for 2 reasons. One, so that we could admire the fact that weren't we lucky that this impact just missed the visitors centre. What a stroke of luck. But no, the other reason for showing this image is to remind ourselves that on the Earth, weathering systems will remove any evidence for really old craters. In other words, this particular crater didn't happen in the last 1 million years or so. If it happened longer ago than that, the traces of this particular impact would have been wiped away by the effects of weathering, the wind and the rain. So you might say, yes, on Earth that will always be the case. Craters will be removed by erosion. But surely on the Moon they will basically last forever. Well, no, actually not. Footprints and small craters will be eroded, not by weathering in the sense of the Earth's atmosphere, but by the consistent bombardment of micrometeorites pulverizing the regolith, the surface soil, if you prefer, of the Moon. So evidence of the Moon landings will eventually be eradicated by micrometeorites. So we can't expect features on the Moon to last forever. On a timescale of 10 to the 7, 10 million years into the future. The pioneers, like Voyager, are leaving the solar system, and the Pioneer probes have a plaque on them. This is what the plaque looks like. There's us up against the outline of the probe, and a little schematic on the bottom showing that we came from the 3rd rock from the Sun of this particular solar system. And the solar system can be located according to the pulsar map on the left-hand side there. So what's happening on a timescale of 10 to the 7 years? Remember, it only takes 30 to 40,000 years for the spacecraft to find the next solar system and fly through it. But on a timescale of 10 to the 7 years, it's thought that the plaques on the Pioneer spacecraft will be unreadable because they will be pitted, because they're flying through the interstellar medium, which is not empty. It's a very good vacuum, but it's not empty. It's full of tiny dust grains. And over millions of years, those dust grains will impact the plaque and ultimately will degrade it and corrode it to the point where it's unreadable. So on a timescale of 10 to the 7 years, Pioneer will have flown through hundreds, if not thousands, of solar systems. And if it's picked up during that transit, then people will read this plaque. But if it's not picked up in the first 10 million years, it might continue to go through other solar systems, but anybody that picks it up from that point onwards will not be able to read the plaque and will not be able to figure out where Pioneers came from. On a timescale of 10 to the 8, 100 million years into the future, we can ask what is going to happen to Saturn's rings. But perhaps first we should ask ourselves, where did they come from in the first place? It's possible that the destruction of a moon such as the Mimas, when we look at Mimas we see an interesting looking moon, you might think to yourself,
that's no moon. It's a space station.
Because it does look a little bit odd, but it's thought that maybe if you take the amount of matter in a moon like Mimas, is it possible that a moon like that, if somehow pulverized, for instance by a collision with a comet, what would happen to all the debris from the moon? You might initially think, well, if you pulverize a moon, then surely the cloud of dust, the cloud of debris, will simply continue to orbit around the planet. But actually, a calculation, a simulation here, shows that if you pulverize a mass similar to the mass of Mimas, what actually happens is the material gets spread out very rapidly. Look at the timescale in the bottom right. It only takes a matter of days for the individual particles of debris, because they're all interacting with each other, because they're continually colliding with each other, it doesn't take long before all the debris gets spread out over the whole of the orbit of the original moon. A few days to make the rings, and then over millions of years, all of these particles continue to slowly migrate inwards because they are all colliding with each other all the time. They are not, in that sense, completely independent. And this process is continuing. And it's been calculated that on the timescale we're talking about, 10 to the 8 years, the individual particles of the ring system will continue to migrate inwards. And on this sort of timescale, essentially, they will all have migrated inwards and rained down onto the surface of Saturn. So in 10 to the 8 years into the future, we may not have any rings of Saturn at all. So for those of you who like looking through a telescope at the rings of Saturn, get in now, because you won't be able to do that in another 100 million years. When we're thinking about the solar system, we again ought to remind ourselves that although we think of the solar system as being like clockwork, orreries, whether they be clockwork or motorized, or tellurians, showing us how the moon goes around the Earth and the Earth goes around the sun. When we look at pieces of clockwork like this, we can fool ourselves into thinking that the solar system is clockwork. We know where the planets were thousands of years ago. We know where they're going to be thousands of years from now. But we can't predict where they're going to be on a timescale of millions or hundreds of millions of years into the future. Basically, on this timescale, the solar system is a chaotic system. Much like the weather, we can predict the weather a few days ahead, but we can't predict the weather months ahead. It's the same idea. We can predict where the planets are going to be thousands of years into the future, but not hundreds of millions of years. In fact, not only can we not tell where Jupiter is going to be in the solar system, we don't even know how many planets there are going to be in the solar system. On this timescale, it might be that a big bully like Jupiter decides to eject one of the smaller planets out of the solar system. It might have happened in the past. It could easily happen in the future. Still on a timescale of 100 million years into the future. This is a schematic of what we think the Milky Way looks like, and there's where we are. There's the "you are here" sign. Currently, we are sitting in between two relatively dense spiral arms. We're in a relatively depopulated part of the Milky Way, a low density region. But as we move around the centre of the Milky Way with all of the other stars on timescales of order 10 to the 8 years, we are going to move into a higher density region of a spiral arm. That means we will have a lot more stellar neighbours. At the moment, we haven't got many stars within, let's say, 10 light years of us. But we think that's going to change when we move into a spiral arm of the galaxy. So what are the consequences of having a lot more stellar neighbours? Well, one consequence we've already sort of mentioned. When Gliese 710 gets close to us in 1 million years or so, it will distort, it'll interrupt the orbits of objects in the Oort cloud and send them raining down. So we're going to have a lot more asteroid or cometary impacts. And indeed, we can see that to some extent in the records. If we look at how many species have become extinct as a function of time over the last 500 million years or so, we see these spikes. Quite a few, 6 spikes over the last 500 million years or so. So it's not absolutely regular, but roughly speaking, once every 100 million years, we get a spike. The last big extinction was the so-called KT extension on the right-hand side there. It was at the boundary between the Cretaceous and the Tertiary periods. That's the impact that killed all the dinosaurs. And we think that we're due for another one on a similar sort of timescale. Because we'll have many more stellar neighbours, we're likely to be hit by something much more than we are in the near future when we have very few stellar neighbours. So this, of course, is just an artist's impression. We don't know what it's going to look like, but if a big rock like that does start to hurtle towards the Earth, from the looks of it, if you look to the left-hand side, it looks like it's heading for Italy. Well, yeah, that's bad news for Italy, but if the rock is big enough, it is going to be bad news for the entire Earth. It's going to disrupt the ecosystem to such an extent that there will be extinctions of lots of species. The real question is, will one of those species be us? Well, we've got a little bit of time to figure out if we are going to see these things coming. Do we have time to deflect them away from Earth to save ourselves from the impact of a large rock like this? That's one of the consequences of having lots of stellar neighbours. Impacts are more likely. A second consequence of having lots of stellar neighbours is that one of those stellar neighbours may decide to go supernova. At the moment, because we've got so few neighbours, we can look at those neighbours, and very few of those stars, virtually none of them close to us, are very massive stars. They don't appear to be candidates to go supernova. But when we have lots more neighbours, maybe we're much more likely to have one of those neighbours go supernova. It's been calculated that a supernova within approximately 100 light years would be a danger to Earth in terms of the amount of radiation it would produce. Remember, when a star goes supernova, it generates more radiation than the rest of the galaxy put together. This is a really serious event. It's been calculated that if a supernova goes off within 20 light years of us, the radiation levels might be high enough to end all life on Earth. And if that sounds a little bit alarmist, bear in mind that we know that supernovae have gone off in our vicinity before. Supernova within about 100 light years leave deposits of a certain isotope of iron called iron 60 in the Earth's sediments. Now, iron 60 is made in supernova and, as far as we know, is not made anywhere else. The iron 60 decays, or changes if you prefer, it changes from iron to cobalt to nickel over a period of a few million years. That means if we see it in the Earth's sediments, it can't have been there when Earth was made. It can't have been there for billions of years. Because it decays into other elements on timescales of millions of years, if we see it in the Earth's sediment, it must have arrived only a few million years ago. So we know that we have in the past had neighbours within 100 light years. That's estimated as the distance. Anything closer could have deposited iron on the Earth. Anything further away, it's unlikely it would have deposited any significant amounts of that particular isotope in the Earth's sediments. So we know it's happened before. It's quite possible it will happen again. All of this time, over the last 100 million years that we've been thinking about, the moon has continuing to tug on the Earth and slow the Earth down. The Earth's spin is slowing, because the moon is robbing the Earth of some of its angular momentum, some of its spin if you prefer, and the moon is taking that angular momentum and increasing the size of the moon's orbit. That's a process that arises because of tidal friction. At this point, 100 million years into the future, the length of the day has now stretched from 24 hours to 25 hours. It's now pointless to try and think about adding leap seconds to our clocks to try and keep the clock synchronized with the Earth. We may as well just forget 24 hours and start decimalizing the day. But a consequence of not the Earth slowing down, but a consequence of the moon moving away from the Earth, well, there's two consequences I can think of. One of them is that the distance from the Earth to the moon will eventually be so large that after 1 billion years or so, it'll no longer be possible to observe a total eclipse of the sun from the surface of the Earth. At the moment, we have this lucky coincidence that as seen from the surface of the Earth, the disk of the moon can cover the disk of the sun and hence give us a view of the corona when the sun's light is blocked out. If the moon is further away, the moon's disk will appear to be smaller and it won't be large enough to cover the disk of the sun. So we will still have partial eclipses and we would still have annular eclipses where the sun's light still peaks around the outside of the disk of the moon. Annular and partial, but no more total eclipses of the sun. That will be a shame, but the second consequence of the moon moving away from the Earth is more serious, and that is the moon has a stabilizing influence on the tilt of the Earth's axis, otherwise known as the obliquity. So the tilt of the Earth's axis has been about 23.5 degrees, give or take a degree, and it's been that for a long, long time. That little cartoon on the left shows you that the tilt of the Earth hasn't really changed much throughout historical records that we can get from geology. And part of the reason for that, the main reason for that, is the moon has been close enough that its angular momentum couples with the Earth and stabilizes the Earth's axis. But if the moon moves further away from the Earth, for instance, once the moon is 25% further away from the Earth, it's thought that it will no longer lock the Earth's axis at 23.5 degrees. The Earth's axis will then be free to flail around like it, well, any way it wants to, basically, and there will be then wild variations in the Earth's climate. So that will be a serious effect in 1 billion years' time. Voyager's gold disk, like Pioneer had a plaque, Voyager's have a gold disk. And on a timescale of 10 to the 9 years, substantially longer than Pioneer's plaque, it is thought that Voyager's gold disk will survive for about 1 billion years. There it is on the right-hand side, a phonograph that can be played to listen to messages and sounds from Earth. Why do we think the Voyager disk is going to last longer than the Pioneer plaques? They're both going to get eroded, but Voyager will last for 10 to the 9 years simply because the disk itself is protected underneath a cover. There's a cover over the top, and the cover is going to take most of the hits from the small particles of dust that are throughout the interstellar medium. That's good in terms of protecting the disk, but unfortunately, if the cover becomes unreadable, it's the cover that contains the instructions for how to read the disk. But bear in mind, on a timescale of 10 to the 9 years into the future, Voyager will have flown through thousands, if not tens of thousands of solar systems in its journey through the galaxy. If it's picked up on a timescale of less than 10 to the 9 years, people will be able to read the instructions. If it's picked up on a timescale greater than 10 to the 9 years, the cover will probably be unreadable, even if the disk itself is still, in principle, not quite pristine, but still as good enough to actually play. Perhaps if anybody picks it up on this sort of timescale, even if they haven't got the instructions, perhaps they'll be intelligent enough to figure it out for themselves. Still on a timescale of 10 to the 9 years into the future, the sun is going to start its journey towards becoming a red giant. As it moves towards the red giant phase, the sun's luminosity is going to increase. something like maybe 10% increase for every billion years as it's going through this phase of its life. That means the Earth is going to heat up, and the greenhouse effect is going to drive the Earth to a relatively balmy 80 Celsius on the surface. That means the oceans are basically going to boil dry. And it's not much point going underground because that's just going to be unbearably hot as well. Perhaps at this point we're going to have to leave the Earth and come back later once it's cooled off a little bit. But as the sun does go towards becoming a red giant, the sun is going to expand until its radius is comparable to the orbit of the Earth. So if the surface of the sun comes towards us, perhaps this is going to be a problem. Are we going to survive this? Is the Earth going to be engulfed? Well, it does seem very likely that the size of the sun is going to increase until it's larger than the orbit of the Earth. But some people think, well, maybe the Earth won't actually be engulfed by the sun. And that's because as the sun expands, as it becomes a red giant, there'll be a very strong solar wind and the sun will lose mass. If the sun loses mass, the gravitational pull on the Earth will decrease and the Earth will move away. It will go to a larger orbit. So the little cartoon on the left shows what might happen. As the sun grows in size, the Earth's orbit will take it further and further away from where it used to be. So yes, eventually the sun will engulf the original Earth orbit, but now the Earth will be somewhere else. Perhaps it'll be out somewhere towards the orbit of Mars. So perhaps the Earth will survive. The jury is out on that at the moment. If the Earth does survive the sun going through its red giant phase, once the sun has been through the red giant phase, it'll come back to being a white dwarf. The outer part of the sun, the outer atmosphere, will slough away and produce a planetary nebula, and what's left will be a white dwarf, a relatively small white dwarf about the size of the Earth. So now we're talking about timescales of many billions of years into the future. If the Earth survives the sun going through a red giant phase, it has another problem to contend with. And that is that the Earth is going to lose its magnetic field. Earth has a magnetic field because the core is molten, and the core is molten not because of any radiation from the sun. The Earth's core is molten because of radioactive decay of elements that have been there for billions of years. But eventually the heat of those radioactive elements radiating heat into the core, eventually the heat will not be enough to keep the core molten. As soon as the core freezes, we no longer have a molten metal dynamo making a magnetic field. As soon as we lose the magnetic field, we're then exposed to radiation from the cosmos. It's thought that maybe Mars went through a similar situation a long time ago. Mars is a lot smaller, its core would have cooled even faster. Perhaps it lost its magnetic field because its core froze a long time ago, and because it lost its magnetic field, its atmosphere was stripped away, and then we have the barren surface that we see today. So perhaps something similar is in store for the Earth on this timescale. They say bad things come in threes. If we survive the sun going through a red giant phase, if we survive the loss of a magnetic field, then we have a third problem to deal with. And that is, on this timescale, the Andromeda galaxy is going to come crashing into the Milky Way. So for those of you who like your astrophotography and you like taking pictures of Andromeda with a telephoto lens, if you wait for a while, the Andromeda galaxy is going to come close enough that you won't need a telephoto lens. In fact, after a while, you're going to need an extreme wide-angle lens to get the whole thing in as it comes towards us. It's thought that when the Andromeda galaxy and the Milky Way galaxy collide with each other, it's unlikely that individual stars are going to collide with each other. So the sun is not likely to hit a star in Andromeda. The sun might be pulled out of the Milky Way. If it does get pulled out, all of the planets are going to go with it. So it's not cataclysmic as far as the Earth is concerned. all of the dust and gas of one galaxy is going to collide with all of the dust and gas of the other galaxy. And so there's going to be an absolute riot of new star formation as these two galaxies pass through each other. To start with, the Andromeda Galaxy is going to pass through and come out the other side, very much distorted. It will lose its spiral arms, we will lose our spiral arms, and eventually we'll settle down into one mega galaxy. For a while, it might be that there are two centres to the galaxy, because there will be a supermassive black hole from the Andromeda Galaxy and a supermassive black hole from our galaxy. It'll take a while for those black holes to merge together. But, as I say, not necessarily cataclysmic for the Earth. We would probably survive such an encounter. On a timescale of 10 to the 11 years, so we're talking now 100 billion years into the future, the little dance between the Moon and the Earth will effectively come to an end, because the Earth will have slowed down so much that one day is now equal to 1 month. In other words, the length of time it takes the Earth to rotate once on its axis is now the same as the length of time it takes the Moon to go around the Earth. So they're now tidally locked together. One face of the Earth is always facing the Moon, and one face of the Earth never faces the Moon. It's a mirror image of what's been happening on the Moon. Of course, we only see one face of the Moon. We never see the far side from the Earth's surface. The same will be true if you look at the Earth from the Moon at this point into the future. And just out of interest, this picture on the right is not photoshopped. That's a genuine picture of the Earth and the Moon taken from a long way beyond the far side of the Moon. That's why it looks a little odd, because we don't normally see the far side of the Moon. We obviously usually see the near side. So it might look like a chocolate digestive biscuit, but it is actually a genuine picture of the Moon sitting in front of the Earth. We're now moving 10 to the 12, 1 trillion years into the future. We've already said that the Andromeda Galaxy on this timescale will have collided with the Milky Way. If we look at what's going on in the immediate vicinity of the Milky Way, we see there are lots of small galaxies around. The local group, the group of galaxies that all gravitationally bound to each other, we have a few big galaxies and a lot of really small ones. Dozens, if not hundreds, of really small galaxies. You can see them there on the right-hand side. The Milky Way is going to hoover all of those up, and we've already said that we are going to collide with M31. Eventually, M33, the Triangulum galaxy, is going to join the fray as well. Basically, the entire local group will end up collapsing into one large mega-galaxy. This icon, take that as just an icon, it's not actually going to be a spiral galaxy. It will probably be one large elliptical galaxy containing everything currently in the local group. What about more distant galaxies? Well, we know the universe is expanding, and as far as we can tell, will continue to expand. Even now, this was a lockdown challenge that I tried a little while ago. Back in 2020, I had a lockdown challenge to try and image a very distant galaxy. I imaged a galaxy that's receding from us at twice the speed of light. Because of the expansion of the universe, some galaxies are being taken away from us with recession velocities that exceed the speed of light. The expansion of the universe is allowed to do that. It doesn't violate anything Einstein had to say. So we know that at present it's possible to see very distant galaxies. And for instance, the picture on the right, one of the Hubble Deep Field images, that's showing a lot of very distant galaxies. Some of them might be close, but a lot of them are very distant. And again, quite a few of those galaxies are currently receding from us at speeds greater than the speed of light. But it's interesting to note that if we go forward 10 to the 12 years, and extrapolate what we think is going to happen from the current expansion of the universe and ask where will the universe be in another 10 to the 12 years, well, galaxies will be so far apart, it's been calculated that they will essentially all be beyond our horizon. In other words, although at the moment we can see 1 trillion galaxies or so, on this timescale they'll be so far away because of the expansion of the universe they won't be visible. So we can either say, what if we had a Hubble Space Telescope in 1 trillion years from now? Or ask ourselves, what if a civilization comes into existence 1 trillion years from now and builds themselves a really fantastic telescope and looks out into the universe? What will they see? What will their conclusion be about what the universe is made of? They will see nothing other than the stars and objects in their own galaxy. They will see nothing beyond their own galaxy, because all of those galaxies will be taken beyond their visible horizon. It's sobering to realize that no matter how good their technology, they will come to the conclusion that the entire universe is just their own galaxy. It took us a little while to realize that wasn't the case for us, but for them, it is something they will never be able to figure out. A sobering thought. Back in November, I told you about the beginning of everything and told you that it took 3 minutes to make all of the hydrogen in the universe. Okay, it made a bit of helium as well, but essentially all the hydrogen in the universe was made in 3 minutes. Since then, that hydrogen has been used to make stars. But after 1 trillion years or so into the future, the hydrogen is starting to run out. If there's no more hydrogen, there's no more new star formation. Now, just as a little bit of an aside, some people have questioned that conclusion. They've said, well, okay, there's no more hydrogen in the future, but is it actually possible to make stars out of something else? We believe that the only real way of making stars is to start with hydrogen and then build up and up and up into heavier elements. But some people have said, might it not be possible to start with heavier elements and make stars from heavy gases? Some people have calculated that it might be possible to have a star with nuclear reactions in the core, but very low surface temperatures. Temperatures much lower even than, for instance, a red giant, which has a surface temperature lower than our sun, only a few thousand Kelvin. Maybe it's possible to make a star with a surface temperature of only a few hundred Kelvin. Is it possible to make a star with nuclear reactions at the core, but an atmosphere in which it's possible for ice to form? Is it possible to make a frozen star? Now, when I say a frozen star, I'm not thinking of the Disney version of Frozen and that image on the left-hand side there. If that's the picture you've got in your head, then let it go, because what I'm talking about is stars with nuclear reactions at the core, but ice in the atmosphere. Some people think that's possible. A lot of people aren't really convinced. But before we can really go any further, and yes, we do want to go beyond the red rectangle there at 10 to the 12, if we want to go any further into the future, we've got to ask ourselves what the expansion of the universe is going to look like. So we can have an idea of relative size on the vertical axis versus time on the horizontal axis. And now is indicated by the line or the circle there. The relative size of the universe is 1, and that's where we're sitting, inside the black circle. The 4 coloured lines are all different because the universe will behave differently in terms of what size will it be as a function of time, either in the past or in the future. It'll depend on how much stuff there is in the universe. Notice that the age of the universe, when did the Big Bang happen? That depends on how the universe is expanding, and that depends on how much matter there is in the universe. For instance, if we take the orange line, if there's an awful lot of matter in the universe, then gravity will grab a hold of that matter and start to put the brakes on the expansion. And we would follow the orange line, which means we would expand and then stop expanding and end up with the entire universe coming back together again into a big crunch many billions of years into the future. That would happen if we have an awful lot of mass in the universe, but we don't think we have an awful lot of mass in the universe. When I was a lad, we used to think that we were on the green line, where the universe will expand and slow and expand and slow. It will keep expanding, but it will get slower and slower and slower. But we now think we're actually on the red line. We're not in a closed universe, which is what the orange would be. We think we're on the red line. And notice what that means in terms of expansion. Not only is the universe going to continue to expand, but notice that the red line is getting steeper and steeper and steeper. And we don't really know why, and we know of no reason why that expansion is going to stop. So to the best of our knowledge, the universe will continue to expand, and the expansion will continue to accelerate. It might be that in the future we get more evidence that gives us a different model for the universe, but at the moment that seems to be the best model that fits the facts. So, in order not to take up your time until gone midnight, I'm going to change the scale at the top of the screen there. Notice the numbers are now much, much bigger. Having gone from 1 to 12, we're now going to much, much, much bigger numbers. Each small box represents 1,000,000 times further into the future than the previous box. So instead of 1,000,000 and 1,000,000,000 and 1,000,000,000,000 years into the future, we're now talking about a zillion years or a gazillion years, or I don't even know what words we use. These are ridiculously long timescales into the future. So where did we leave the argument before we took this little aside and ask ourselves about how the universe is expanding? Well, we said that it took 3 minutes to make all the hydrogen in the universe, but the hydrogen is running out. Now, some stars might last an awful long time. Some stars have lifetimes that's measured in trillions or tens of trillions of years. But stars don't last forever. So if the hydrogen is running out, what does that mean? There will come a time when the age of starlight comes to an end. There will be no more stars shining, no more nuclear reactions keeping the stars hot. What's left will still continue for a while to orbit their galaxies. These dead husks of stars will still be drifting through space like zombies, white dwarfs, neutron stars, black holes. It might be odd to put white dwarfs into the same category because you say, well, white dwarfs are white, they're shining, aren't they? Well, not in the sense that nuclear reactions are keeping them warm. White dwarfs are only white because they start their life at the death of a star as rather hot objects, but then they cool down. With no nuclear reactions to keep them hot, white dwarfs will relatively quickly cool down and basically become black dwarfs. Just lumps of matter sitting in space, not shining. We think that stars will either be ejected from the galaxy or might conceivably be eaten by the central supermassive black holes. When we look at other galaxies and map out what we think is going on in other galaxies, it's possible to look at the magnetic fields which tell us, we think, how matter will be funneled into the supermassive black holes in the centre of the galaxy. This galaxy on the left-hand side, the magnetic fields have been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy. That's the one with a big telescope in the back of a 747. And we think that matter is funneled down these magnetic field lines into the black hole. That's how the black hole in the centre feeds on all of the gas and the dust and the stars when we get to this very long time period of 10 to the power lots, 10 to the power 30 at the moment, years into the future. What happens to individual atoms we're not actually too sure about. At the moment, the picture we have of atoms is we have a positively charged nucleus and negatively charged electrons buzzing around, and the positive charge in the nucleus comes from the protons. Now, it is not known what happens to protons on the longest of timescales. If a proton decays on a timescale of this sort of value, then that means every atom in the universe will fall to pieces. We don't know the timescale over which protons will change or decay, and we don't know if it happens at all, and if it does happen, we don't really know the timescale, other than we don't think it's on a timescale less than 10 to the 36 years. But it might be on this timescale or longer. It might be that protons are not stable. They appear to be stable, but maybe they're not. If they do change, all atoms will disappear from the universe. But even if protons don't decay, atoms will indeed survive for a while longer, but not much longer, because dwarf stars, originally white dwarfs, but now black dwarf stars, they will evaporate. That's a quantum mechanical effect that I'm not going to describe in any detail. But once black dwarfs evaporate, there are no atoms left. There are only neutron stars and black holes, and neither of those contain atoms. So on this timescale, there are no atoms left in the universe. We think that black holes will merge together in much the same way that Andromeda has crashed into the Milky Way, and the black holes at the centres of those two galaxies will merge together. Then we think black holes in other galaxies, clusters of galaxies, superclusters of galaxies that are bound by gravity, eventually all of those black holes will merge together. And they may start off as millions or billions of solar masses, but when they all merge together, we're going to end up with black holes that might have masses of trillions of solar masses. But even black holes are not eternal. They don't last forever. They evaporate, providing that you wait for, as we see here, ridiculously long times, like 10 to the power 66 years. So we can ask the question, why do black holes evaporate? Well, this is something that quantum mechanics allows if we go through the argument in a couple of slides. According to our understanding of quantum theory allows you to borrow energy from nothing, if you like, and make matter and antimatter. You can make a particle and its antiparticle equivalent. In other words, you can make an electron and an anti-electron. You can make them by borrowing energy. Then the two particles annihilate, the particle and the antiparticle annihilate, and you get the energy back again. So you borrow energy and then you pay back the energy. So if you like, you borrow energy, you make stuff and anti-stuff, and then they annihilate and the energy comes back again. Now, how does that relate to black holes? Well, Hawking said, I wonder if this process goes on just outside the event horizon of a black hole. What might happen then? If you imagine that's the event horizon of a black hole, Hawking said, I wonder what would happen if you borrow some energy, make matter and antimatter, one of them falls into the black hole and the other one doesn't. Then what you're left with is it looks like something has come out of the black hole. There seems to be a net flux of particles coming from the event horizon. We now call this Hawking radiation. We haven't seen it from a black hole. It was conjectured by Hawking. Most scientists seem to think, well, this is what quantum mechanics tells us, so that must be what's likely to happen. The radiation increases with decreasing mass. So in other words, large black holes evaporate very slowly. As they get smaller and smaller and smaller, they evaporate faster and faster and faster. And so the radiation levels from a black hole start off very low, but they increase rapidly, and finally a black hole will disappear in a flash of radiation. Even the really big ones, even the supermassive black holes that are trillions of solar masses, they will radiate really slowly, but if you wait long enough, even they will evaporate. It will take trillions of times longer than the smaller black holes, but if you've got enough patience, they will evaporate and leave you with nothing but radiation. So have we reached the end of time? Well, we've reached the end of those numbers, so that's almost the same thing. We would have to go to something like 10 to the power 100, in other words, a Google. No, not that Google. That Google is simply a misspelling of the actual number itself, Google. 10 to the power 100, if we think about what's happening on a timescale of 10 to the power 100 years, it's been calculated that every black hole conceivable, no matter how massive it might be, would have evaporated by this point, by this time. So after this, nothing happens. There is no more matter left in the universe. Everything has been turned to radiation, so there is simply radiation floating around the universe. So the passage of time becomes essentially meaningless at this point. And just to remind us what a silly number 10 to the power 100 years is, let's just write it out just for the hell of it. That's what 10 to the power 100 looks like. 10,000 million, oh, you can do it yourself. It's an awful lot of zeros. And on that timescale, we can't imagine that timescale. However, we can calculate how things behave on that timescale. And we believe that's what we're talking about here, the end of all matter in the universe on a timescale of 10 to the power 100 years. As close to the end of time as we can get. Woody Allen had a good phrase, eternity is a very long time, especially towards the end. And XKCD, one of my favourite cartoons, has an interesting way of trying to put a human perspective on the entire history of the universe. XKCD says that a human is simply a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process, which involves checking email a lot. That's an interesting way of giving a perspective on the human condition. So having said that everything is going to come to an end, that sounds very depressing, so let me finish on a slightly more upbeat note. We could say that we live in an absolutely golden age. The sun is middle-aged and well-behaved. The moon is at just the right distance to stabilise the Earth's axis and hence stabilise the Earth's seasons. And as a little bit of a bonus, it gives us the spectacle of a total eclipse of the sun for a little while longer. Thanks to evolution, we are able to explore and discover and understand the universe in which we live. We can do that by building machines and sending them out to visit our nearest neighbours. And we can also build telescopes that allow us to see billions of galaxies at distances of billions of light years. But we could not have done this in the very early universe. Humankind could not have arisen in the very early universe. We needed generation upon generation of stars to take all the hydrogen and convert it to helium and carbon and nitrogen and oxygen and calcium and phosphorus and iron and all of the elements that make us us. So we could not have existed until the universe had settled down a little bit. And we've just seen that the far future, trillions of years from now, the universe will be dark and the universe will be boring. So you could say the best time to exist is now. Thank you for listening.